to do to bring this charge here. Now I'm going to introduce electric potential. Electric potential. And that is the work per unit charge that I have to do to go from infinity to that position. So Q doesn't enter into it anymore. It is the work per unit charge to go from infinity to that location P. And so if it is the work per unit charge, then this little Q disappears. And so now we write down that V at that location P, the potential, electric potential at that location P is now only Q divided by 4 pi epsilon 0 R. Little q has disappeared. It is also a scalar. This has unit joules. The unit here is joules per coulomb. I have divided out one charge. It's work per unit charge. No one would ever call this joules per coulomb. We call this volts, called after the great Volter, who did a lot of research on this. So we call this volts. But it's the same as joules per coulomb. If we have a very simple situation like we have here, that we only have one charge, then this is the potential anywhere, any distance you want from this charge. If R goes up, if you're further away, the potential will become lower. If this Q is positive, the potential is everywhere in space positive for a single charge. If this Q is negative, everywhere in space the potential is negative. Electrostatic potential can be negative. The work that I do per unit charge coming from infinity would be negative, if that's a negative charge. And the potential, when I'm infinitely far away, when this R becomes infinitely large, is 0. So that's the way we define R0. So you can have positive potentials near positive charge, negative potentials near negative charge, and if you're very, very far away, then potential is 0. Let's now turn to our Venn graph. It's a hollow sphere, has a radius r, about 30 centimeters, and I'm going to put on here plus 10 microcoulomb. It will distribute itself uniformly. We will discuss that next time in detail, because it's a conductor. We already discussed last lecture that the electric field inside the sphere is 0, and that the electric field outside is not 0, but that we can think of all the charge being at this point here. The plus 10 microcoulomb is all here, as long as we want to know what the electric field outside is. So you can forget the fact that it is a sphere. And so now I want to know what the electric potential is at any point in space. I want to know what it is here, and I want to know what it is here at point P, which is now a distance r from the center. And I want to know what it is here at a distance little r from the center. So let's first do the potential here. The potential at point P is an integral going from r to infinity. If I take the electric force divided by my test charge Q dot dr. But this is the electric field. See? It is force times distance is work, but it is work per unit charge. So I take my test charge out. And so this is the integral in r to infinity of E dot dl, dr, sorry. And that's a very easy integral, because we know what E is. The electric field we've done several times, follows immediately from Coulomb's law, and so when you calculate this integral, you get Q divided by 4 pi epsilon 0 r, which is no surprise because we already had that for a point charge. So this is the situation if r, little r, is larger than capital R. Precisely what we had before. We can put in some numbers. If you put in r equals r, which is 0.3 meters, and you put in here the 10 microcoulomb and here the 30 centimeters, then you'll find 300,000 volts. So you get 3 times 10 to the 5th volts. If you take r equals 60 centimeters, you double it. If you double the distance, the potential goes down by a factor of 2. It's 1 over r. So it would be 150 kilovolts. And if you go to 3 meters, then it is 10 times smaller, then it is 30 kilovolts. And if you go to infinity, which for all practical purposes would be lobby 7, if you go to lobby 7, then the potential for all practical purposes is about 0. Because r is so large that there's no potential left. So if I, Walter Lewin, march from infinity to this surface of the Van de Graaff, and I put a charge Q in my pocket, and I march to the Van de Graaff, by the time I reach that point, I have done work. I multiply the charge now back to the potential. That gives it work again, because potential was work per unit charge. And so the work that I have done then is the charge that I have in my pocket times the potential, in this case the potential of the Van de Graaff, if I go all the way to this surface, which is 300,000 volts. If I were a strong man and I would put 1 Coulomb in my pocket, that's a lot of charge, then I would have done 300,000 joules of work by just carrying the 1 Coulomb from lobby 7 to the Van de Graaff. That's about the same work I have to do to climb up the Empire State Building. It's the famous mgh, my mass times g times the height that I have to climb. So, I know how the electric potential goes with distance. It's a 1 over r relationship. Now I have arrived at the Van de Graaff, I am at the surface with